Okay, so this mini lecture is going to look at the idea of moment of inertia. And this actually goes by another name. We call this the rotational inertia. Now, when we first learned about the idea of inertia, remember it was related to an object's mass, and it had to do with resisting a change in motion. Something that had a lot of mass, a lot of inertia, was really hard to get to change its motion. Well, something that has a high rotational inertia is the resistance to change, to a change in rotation. So, how difficult it is to get something to rotate. You're gonna hear the kids in the background on this one. So how difficult it is to get something to rotate. Well, when we think about getting something to rotate, we know we have to exert a torque. We know that force has to be applied at a distance. What influences how easy or difficult it takes to get something to rotate? Well, just like something that influences how easy or difficult it takes to get something to change its motion, mass is certainly going to play a role. The more massive an object is, and the more difficult it's also going to get it to rotate. So, if we think about not only the mass, when we deal with rotation, we also have to think about the axis of rotation. So, two things are going to be important: the mass and the axis of rotation. And as we think about the mass specifically, it's going to be how that mass is distributed along that axis of rotation. So let's see what that means. All right, imagine that you have an object. It's uniformly distributed. We know with a uniformly distributed object, the mass is distributed evenly throughout the entire object. All right. I can rotate the object about 3 different axes. One that runs vertical, so that would look like this, rotating the object along a vertical axis. One that runs horizontal, so that would look like this. The object is rotating about that horizontal axis. And the other that has the planes kind of straight out at you. And that would look like this, so rotating the object around that plane, that axis. Now, if I change the mass distribution, so if I add a clump of something, and if you have Play-Doh or clay at home, you can take a pen and put a clump of Play-Doh or clay on the end of that pen. If I have that pen and I want to rotate the axis, or rotate that object around all three of those axes, how does it now feel? Well, if I look at the axis straight up and down, it's still relatively easy to rotate that object about the axis. The mass isn't very far from the axis. But if I increase the distance that mass is distributed from the axis, so I'm going to rotate about this plane now, it becomes very difficult to change the rotation of that object forward or backwards. If I rotate about this plane, it's very difficult to change the rotation of that object now that the mass is distributed away from the axis. So the further the mass is away from the axis, if I increase the distribution of the mass away from the axis, it is more difficult to rotate. It has a higher rotational inertia. Rotational inertia. So, as I distribute the mass away from the object, it becomes more difficult to rotate. A higher rotational inertia. Now, for rotational inertia, we use a capital letter I as its symbol. Now, you already have experience with this. I want you to imagine walking through a parking lot and you see those parking barriers, little cement balance beams, right, that you see for cars to stop. And you, of course, can't resist that urge to hop up on that balance beam and pretend you're the most elegant gymnast walking along the balance beam. Well, what do you do instinctively? You jump on that balance beam and you do what? Instantly put your arms out, right? That stabilizes you. Well, why? Your axis of rotation is at your feet. I know you can't see my feet. Imagine your axis of rotation is at your feet, okay? And when our arms, so here we are standing on that balance beam, and the balance beam is coming forward and backwards. When our arms are at our side, well, our center, our mass distribution is close to the axis of rotation. You can imagine that if I'm going to fall off that beam, I'm going to fall off the beam. So I'm going to rotate about that axis. Well, as soon as I put my arms out to the side, I've taken some of my mass and I've distributed it away from the axis of rotation. If I increase the distribution of mass away from the axis of rotation, well, I get a higher rotational inertia. It's more difficult to change my rotation. It's more difficult for gravity to tip me over. So that instinct of putting our arms out to the side to stabilize ourselves is really all about this idea of moment of inertia. Increasing the distribution of mass away from the center, making it more difficult to rotate the object. All right, so here's another challenge for you to either try at home, or if you have this object or baseball field or whatever, imagine a baseball bat. So just imagine for a moment that this is a baseball bat. We know that a baseball bat has heavier mass at the end than at the handle. So my question is it easier to balance? Remember we learned about balance, that idea of keeping our center mass above the base. And if we are tipping over, what are we doing? We're rotating. Gravity is causing that torque, is causing that rotation. Would it be easier to balance the baseball bat with the head of the bat way up at the top so our finger is on the handle, or with the head of the bat at our finger and the handle of the bat is up at the top? Thinking about mass distribution and the axis of rotation, which would provide a higher moment of inertia and therefore easier to balance, more resistance to change the rotation, more resistance to tipping over, therefore easier to balance? Well, if you said with the head of the bat up higher, you were right. The mass is further away from the axis, causing it to be more difficult for the Earth to change its rotation, to tip it over. Higher moment of inertia. So balancing the bat like this is much easier than, oh my gosh, balancing like this, which I can't even do. So if you have more mass at the top, actually have a higher rotational inertia. The mass is distributed away from the axis, and it's easier to balance. All right, we're going to use rotational inertia when we talk about rotational momentum, when we talk about rotational kinetic energy, and a lot of different uses when we talk about getting something to rotate by using a torque. But the basic idea is mass distribution relative to the axis, and the further I distribute that mass away from the axis, the higher the rotational inertia I have. All right, good job.